All right, ladies and gentlemen, apparently I got scrambled last week and I gave you last week's lecture this week. First, yes, that's correct. And then this week I'm giving you last week's lecture. So that was my mistake. So let me give you this lecture real quickly. In calculus, we can approximate the area of a curve. So approximation of area is the following lecture. So approximation of area. So in this case, what we have is consider a region bounded by the x-axis and the y-axis. And given the graph, f of x is equal to the square root of 4 minus x squared. So basically, they're giving us the following. Here's the area. Here's basically 1, 2. And this is basically 1. This is 2. And the area of the graph looks at the moment as is being bound as such. So all of this is being bound. Now, the question becomes, as you compute this, how do you determine the area? The other possibility is also to consider if this is a rectangle, such as this, as you can see, this triangle part is not included in the calculation, nor is technically there's a little piece basically up here that also is not included in this part. So all of this is not included in the triangle, and we're trying to approximate this area. So if I'm looking at this particular example, we're going to determine the height of the rectangle by the value of the function on the left endpoint. So if we look at this, we're going to start with 1 times f to the 0 power plus 1 times f to the 1 power, and that's equal to 2 plus square root of 3. And that approximately comes to 3.7321 square units. So note that f of x is decreasing, is a decreasing function. So if you look left to right, it's decreasing. And so we don't want to overestimate the area. We want to stay within the region. So if we look at this again, this function is 4 minus x squared. So if we want to repeat part A, which is the first initial part of the value of the function at the right end to determine the height of the rectangle, we use the right endpoints. In this case, the area of the 2 rectangles is going to be 1 times f of 1 plus 1 times f of 2, which in this case is square root of 3 plus 0, which gives us a perfect value of 1.7321 again. So this is square units. Notice that underestimate the area. So we underestimate the area of the particular region when we use the endpoints, the right endpoints. So in the left endpoints, it gives us an answer too big, and the height of the right answer is a value that is too small. So it is reasonable to assume that the average of the 2 answers could be perhaps the answer we seek. So this produces the method called the trapezoidal method. So in this method, we take the 3.7321 plus the 1.7321, add it together and divide by 2, and this gives us 2.2 2, no, I'm sorry, 2.7. 2.7 gross. Let's get this. 321 square units. So let's do this one more time. Let's take this again and try to repeat the part A, and using the function in the midpoint of each of the intervals and determine the height. So we'll take that same figure, and this being 2, this being 1, and this being 1, and this being 2. And again, this is a very unique value with a decreasing value here. And obviously there's a trapezoid here, and there is another value here. Okay, and so we'll take the midpoint, go right in the middle, and we'll take the average of those heights. And so if you notice, this becomes as a value, this becomes 1 times the f of 1/2 plus 1 times the f of 1/2. And so this becomes square root of 15, square root 15 over 2, plus 7, square root of 7 over 2, which equals approximately 3.2594 square inches. So this gives us a little bit of variation here. If we want to improve the accuracy, perhaps we can do one more thing. We can look at it this way, and this is just looking at the triangle from a series of locations to see which way we could best express it. And again, here's the function, and we have a series of trapezoids. So now we're going to look at this in terms of the half values. So here's 1, here's 2, here's 3, and here's 4. And so in this case, I'm looking at this as 1/2. 1/2 times from the left end, this would be f of 0, plus 1/2 times f of 1/2, plus 1/2 times f of 1, and times, or plus 1/2 of f of 1.5. So this gives me 1/2 times 2 plus 1/2 times the square root of 15 over 2 plus 1/2 square root of 3 plus 1/2 square root of 7 over 2. And adding all that together gives us 1 plus square root of 15 over 2 over 4, sorry, square root of 15 over 4, plus square root of 3 over 2, plus square root of 7 over 4, and is equal to 3.4957. So that gives you a little bit better measure. And furthermore, we can break this down even further. We're still looking at the area between 1 and 2. So here's 1, here's 2, here's 1, here's 2. And now we're going to break it into fourths. So this becomes 1, 2, 3, 4. This becomes 1, 2, 3, 4. Okay, so this is supposed to be a little bit more uniform. So here we go. This will be one trapezoid. This is our second trapezoid. Our third trapezoid. Our fourth trapezoid. Our fifth trapezoid. Sixth trapezoid. Seventh trapezoid and eighth trapezoid. And the idea is we're looking at this as it breaks down. So as you can see, obviously we're missing these parts, right? So there are some parts that are not included. So this is the second example. This would be 1/4 of f of 0 plus 1/4 of f of 1/4 plus 1/4 of f of 1/2 plus 1/4 of f of 3/4 plus 1/4 times f of 1 plus 1/4 of f of 5/4. There's an f here. Okay, plus 1/4 of f of 3/2, and lastly plus 1/4 of f of 7/4. And when you do the math of this value, you obtain an approximate value of 3.3398 square units. So that is the topic where we're trying to round off different ways to exact as approximately to the area as possible. So you can see that if you take values of n, as in the sides, and let's do left sum, let's do right sum, trapezoidal, and midpoint. Okay, and the midpoint would be the last one. And so this value would start with 248. That's the one. 248, let's do 10, let's do 20, let's do 40, 50, 100, and let's do 500. We're then going to look at this from the left side. From the left side, you get 3.721. From the right side, you're getting 1.7321. From the trapezoidal, you're getting 2.7321. And from the midpoint, you're getting 3.2594. And so we repeat this process now. Let's go through a 4-sided trapezoid where we would have 3.4957. You would then have 2.4957, I guess. And trapezoidal, you get 2.9957. And midpoint, you get 3.1839. So you can see that there's some semblance there. So each triangle has a width 2 divided by n, and it's being divided down here. And so these are the values you obtain. So I'll do up to 8. You guys can play with this and see if you want to understand this a little bit better. 3.3398, 2.8398, trapezoidal is bigger at 3.0898. Okay, and lastly, midpoint 3.1567. So my point is, you notice the values are keeping consistent, but the trapezoidal will eventually, if you have 100 as a value, or 500 in this case, this becomes 3.1415. It increases, if you notice. On this side, this becomes 3.1455, and this is a 500, so I'm just showing you. This becomes 3.1375, and this becomes 3.14. So if you notice, they become a little bit closer in alignment to the value of the actual model. So the original model begins with y equals the square root of 4 minus x squared. And if I square both sides, I end up with y squared is equal to 4 minus x squared. So x squared plus y squared is equal to 4. And so in that case, you notice it's a circle, basically. And so if you look at this value, you can actually argue that 1/4 of pi times 2 squared would equivalent to pi, which is about 3.14. So it says the limit at as the number of triangles increase without bound, the sum of the areas of these rectangles get closer and closer to the actual value of the region of pi. So basically, we have the limit as n reaches infinity, the sum of the areas, which is what we're calculating here, this becomes closer to pi. Okay, so this is one of the little tidbits. They also say that in terms of the sum area of the x, sum area of x is approximately b minus a over n. And so we're going to see this in the definite integral problem. So looking at the area here, the area of the rectangle, we are getting that is equal to the sum of f of xi times the sum of x. If I were to tell you that the definite integral is defined as the following: if f, the function, is defined on the interval AB, so there's some sort of interval AB, the definite integral of f from A to B is given by and no, so they give us the indefinite integral, where this is f of x dx is equal to the limit of as n approaches infinity as the sum of n over 1 I equal to 1 of f of x1 times the change of x, provided it exists where the change of x of b minus a over n, and n is any value of x in the ith interval. So we definitely have that. And so in our example, our previous example, our integral was 0, and this would become square root of 4 minus x squared of dx is equal to pi, based on the explanation. Okay. Let me stop here for a minute, and we'll continue shortly.